Welcome to our comprehensive lecture on AC motor drives and variable frequency drives, commonly known as VFDs. Today, we are going to explore how we control the workhorses of modern industry, electric motors.
Every motor needs a controller. The simplest is the across-the-line starter, which just slams full voltage to the motor, causing a massive spike in current. Soft starters improve on this by ramping up the voltage smoothly, but the ultimate control comes from a VFD, which gives us precise command over both speed and torque.
So, how exactly does a VFD control a motor? It actually changes the nature of the power. It takes the incoming AC power, converts it into a smooth DC voltage, and then uses fast-acting switches called IGBTs to chop that DC power into a pulse width modulated waveform. To the motor, this looks like a custom AC wave where both voltage and frequency are perfectly controlled.
Before selecting a drive, you must understand what the motor is physically moving. Constant torque loads, like conveyors, need the same twisting force whether moving fast or slow. Variable torque loads, like fans, need exponentially more power as they spin faster. Getting this right is crucial for sizing your VFD.
When it comes to sizing, horsepower is helpful, but full load amperage is king. You must ensure the VFD can continuously supply the amps listed on the motor's nameplate, plus a little extra headroom for overloads. You also have to factor in the environment. Drives generate heat, and if they are in a hot room or at a high altitude, they need to be derated or upsized. VFDs come in different classes to match your application and budget. Microdrives are tiny, but surprisingly powerful for small tasks. General-purpose drives hit the sweet spot for most factory floors. If you need extreme precision, you step up to high performance. And if you are in a food plant where equipment gets hosed down, you'll need a sealed NEMA 4X drive. Once installed, how does the drive actually regulate speed? Volts per hertz is the standard, simple method, great for basic pumps. Sensorless vector is smarter. It calculates what the motor is doing based on electrical feedback. But for the ultimate precision, closed-loop flux vector uses a physical sensor on the motor, allowing it to hold a heavy load perfectly still at zero speed. Sometimes speed isn't the goal, force is. In torque control mode, the VFD modulates power to maintain a specific tension. Think of a machine winding delicate tissue paper. As the roll gets fatter, the speed must change, but the tension must remain perfectly constant so the paper doesn't tear.
What happens when a heavy load needs to stop fast? The motor acts like a generator, pushing power back into the drive. Dynamic braking solves this by burning off that excess energy as heat through a resistor. To control that stopping precisely, we use encoders, which send hundreds of tiny digital pulses per revolution back to the drive.
To make a VFD part of an automated system, it needs to talk to a controller. You can use simple hardwired analog signals, but modern systems rely heavily on industrial Ethernet. Protocols like Ethernet IP or Profinet allow a central PLC to send complex commands, monitor power usage, and read fault codes all over a single network cable. Even the best VFD will fail if the system is designed poorly. The most common mistakes include sizing based on horsepower instead of amps, stuffing the drive into a tiny unventilated box where it overheats, or running sensitive network cables right next to the noisy motor power wires, which scrambles the communications. To wrap up, remember that successful motor control starts with understanding the load. Always size your VFD based on full load amperage, choose the right control mode for your application, and ensure your installation accounts for heat and electrical noise. Thank you for joining this lecture on AC motor drives.